Hello everyone. In this video we're going to do one example. What I'm going to do is verify the group actions completely in one example. So I'm going to give you a set, I'm going to give you a binary operation, and then we're going to check that with this binary operation this is a group. So let's go ahead. So what is the example? Let S be the real numbers except the number -1. So all the real numbers except -1, and I'm going to define an operation on a binary operation on S such that for every A and B, A star B is A plus B plus AB. And the exercise is to prove that S under star is an abelian group. So let's go ahead. I'm going to switch to black for the proof. And the very first step is to show that S is closed under star. So what we need to know is that for every A and B in S, so every number that is not -1, A star B is also in S. So we have to check that A star B is not -1. So let's see what would happen if A and B are in S, so they are real numbers except -1, and A star B, so A plus B plus AB is -1. If so, then A plus AB would be minus B minus 1, which is -1 plus B. And on the other hand, this is A times 1 plus B, and therefore we get that A times 1 plus B is -1 plus B. But B is not -1, and that implies that 1 plus B is non-zero, and therefore I can divide by 1 plus B, that's a real number, and what I get is that A would be -1 plus B divided by 1 plus B, so it would be -1. So that is a contradiction because A is in S. So this is impossible. Okay, so that arrow is impossible. Let me maybe call it this step is impossible, and therefore A star B is in S. Okay, so the operation is closed in S. What do we have to check next? Next, we have to check the first axiom, which is the fact that the operation has to be associative. So let A, B, and C be in S, so real numbers that are not -1. And let's start with A star, B star, C, and see how much that is. So that would be A star times B star C is B plus C plus BC. And A star something will be this plus the product. So A plus B plus C plus BC plus the product of A and this, A times B plus C plus BC. So if we simplify all of this, this is A plus B plus C plus BC plus AB plus AC plus ABC. And now you see that where I got this is symmetric in A, B, and C. So this is, I have A plus B plus C. I have all the combinations of A, B's, and C's in pairs, and I have the triple product. So because this is symmetric in A, B, and C, it doesn't matter if I do sort of permutations of the letters A, B, and C, I know that it is going to work out. But let's just do it for fun. so how much is A star B star C? A and B together will be A plus B plus AB, and then star C, that will be A plus B plus AB plus C, plus the product of A plus B plus AB and C, and then I get A plus B plus C, this C, and then plus AB plus A times C is plus AC, B times C is plus BC, and AB times C is plus ABC. And this, let's call this 1, this is equal to 2, and therefore the star is associative. Great. So that's the first axiom of group. So now let's try the second axiom. I need an identity element. So I need that for every, I know that there is some element E and S, such that for every A in S, we have A star E is the same as E star A is A. So what could be that number? So I'll go to some sort of like thought bubble here, and I'm going to try to figure out what E should be. So E should be, well, A star E is A plus E plus A times E, and I need this to be just A. Then that tells me that, well, E plus A times E has to be 0. And the possibilities are, well, this is A times, this is E times 1 plus A equals 0. But the possibilities now are either A is minus 1, but that is not possible because A is in S, so A is not minus 1, or E is 0. So 0 works. So so I need to check that there is an E in S that does that job. So if I take E to be 0, which is in S, remember S is just the real numbers except the number minus 1, so 0 is in there, then what happens with A star 0? That will be A plus 0 plus A times 0, which is A, and 0 star A is 0 plus A plus 0 times A, which is A. So it works as an identity element. Okay, so now I have the neutral element, and now I need multiplicative inverses or star inverses. So I need that for every A in S, there is some A inverse in S also, such that A star A minus 1, A inverse times A will be the identity, which I know now it's 0. So I go back to my thought bubble and try to think, what is that going to be? So if A star A inverse is 0, and A star A inverse is A plus A inverse plus A times A inverse, then what I need to do, if this is 0, I need to solve for A inverse. So this, I can take a common factor of A inverse on this side, and that gives me 1 plus A, and bring this A to the other side. So A inverse has to be minus A divided by 1 plus A. Now, A is not minus 1, so that denominator is non-zero. That's good. But what if this was minus 1? What if minus A, 1 plus A is minus 1? Then that would not be part of S, and I would be in trouble. So let's see what would happen in that case. In that case, I have minus A is minus 1 minus A, and it would tell me then, these cancel out, that 0 is minus 1. Which is not going to happen. in the real numbers, so we are safe. So then, indeed, there is such a thing as A inverse. Let A inverse be minus A over 1 plus A, and note that minus A, 1 plus A is not minus 1, or 0 is minus 1, which would be a contradiction, so that's not happening. So it is not minus 1, so minus A over 1 plus A is an element of S. And let's check that it works as a multiplicative inverse. So let's multiply A times A inverse with star. That will be A star minus A over 1 plus A. That is A minus A 1 plus A plus the product of A and this. So I get minus A squared 1 plus A. Wow, let's see, what is this? So this is going to be a common denominator of 1 plus A, and then 1 plus A times A, minus A squared. But this over here is, so this is A plus A squared minus A squared over 1 plus A, and everything cancels, and I get 0. So I get that the product of the two gives me 0, which is the identity. And same, this exact same thing happens with A inverse and A. I do get 0. Okay, and I'll emphasize once again that this is a symbol for the inverse with respect to a star. So this is not 1 over A. Okay, this is the symbol for what the multiplicative inverse is going to be, which in this case takes that form, minus A divided by 1 plus A. Okay, so this checks that G or S under star is a group. So S under the star is closed under star and satisfies G1 through G3. It is associative. There's a neutral element, and there are inverses with respect to star. So now we need to check. So this tells me that it is a group. So now I need to check that it is an abelian group. Check that this is abelian. Well, I need to check that for all A and B in S, we have that A star B is the same as B star A. But since A star B, well, which is true, because A star B is A plus B plus AB, which is the same as B plus A plus BA, because which is B star A. And from here to here, we've used the fact that addition is a group, is a commutative operation, and multiplication is also commutative operation on the real numbers. So we get that A star B is B star A, and therefore S star is an abelian group. And that's the end of our proof. Okay, so that's a full example of how to verify that something is a group, an abelian group in particular.